Hey, welcome. Welcome to this performance analysis session. My name is Simone. I work for an American company called Webtide. We offer services and support around a now old open source project called Jetty. And Jetty is now, this year is 29 years old. It's probably the oldest open source project in the Java sphere. It was initially started by Greg Wilkins, the founder, as a issue tracking tool. But in order to have a web application that was capable of doing issue tracking, it needed a web server. And so he started writing a web server, and then from there on, Jetty became one of the most used Jetty services around. Just a couple of words about Jetty. We just released version 12, and version 12 is a new, let's say, rewrite of the core engine of Jetty, because now we're able to run inside the same version of Jetty. We are able to run EE8 applications, so all those that were based on JavaX.servlet or JavaX APIs in general, so REST and whatever. But also you can deploy in the same instance also EE9 applications, so Jakarta.something, and also the new EE10 ones. And we are working also on the new upcoming EE11 specifications. So you have a single server where you can actually use and deploy in it your old applications that you do not want to do the effort of porting them into the Jakarta space. They're still JavaX, but you still can deploy them in Jetty 12. And you develop new applications, and you will be able also to develop and deploy new Jakarta applications inside the same instance of the Jetty server. On the side, we have a client. We're working on the new stuff that is coming up with HTTP3 as well. And so it's an exciting project that we're always trying to, stay on the top, even after 29 years. And it's really exciting because there's always new problems to look around. So this session basically came about because during the development of Jetty 12, we had a number of problems to solve, and many of them were related to performance. So we also, as a consulting that we do with our company for clients that use Jetty, we help customers to understand the performance behavior of their own system. So they write a web application, they try to run a load test, and they say, oh, does it perform well? Or it doesn't perform as I expect. Where's the problem, right? So this session came about, and we will give you a few war stories, examples of what happened to us and to clients about, things related to performance. So what is you have written a web application, right? And how does it perform? And well, like many of this type of questions in our field, the answer is, well, it depends. Because the real thing that you need to think about is you have to ask yourself the right questions. And the right questions can be really different. And so, for example, here you get, what is your end goal? Because why do you measure performance? What is it that you really need? It's not the performance per se, because if you get a number out of it and you say, oh, my web application does 100, well, that's a number that is not really useful per se. It is useful if you say, well, it does 100, therefore it means that I need this many machines in order to sustain the load that I'm supposed to sustain when I put the machines in production. Or you want to have an answer for your boss, for example, and it says, comes to you and say, hey, let's say Black Friday is coming. Can the system sustain the load that we expect to be maybe 10 times the normal usage? And then you have to give an answer and say, yes, it can sustain the load. We have these strategies to cope with the load, or no, it can't. We need to prepare. Or you want to work for, have an answer and say, okay, I want my application to have minimal latency, or I want my application to be as efficient as possible. For example, do very little allocation, or having very little lock contention, and so on and so forth, right? So you need a question like an end goal to solve, and then you do load testing, because that's the way that you try to test the performance of your web application. Now, this is kind of funny because many people open an issue to Jetty and they say, hey, I have done load testing to Jetty, doesn't really perform well, and say, okay, how did you do load testing? And then they said, oh, well, I just written a for loop, and inside the for loop, I do a blocking request to the server, and the server can only do 100 requests per second, or whatever the number it is. Well, but that's a completely flawed load test because obviously it's limited by the client, not by the server. So they claim that Jetty cannot do more than 100 requests per second, but actually it's the client. It's a single thread sending a request, blocking, waiting for the response, and fundamentally the server says, oh, I'm replying immediately and then I'm waiting for you to send me the next request. But most of the time the server is just there idle. It can do a lot more than that, but if you measure just at the client, you don't see it. So in our experience, we have found a couple of different terms to indicate load testing. One, we call it the steady state load testing, and the other one is the limit load testing. They're both useful and they both answer different things. In particular, for the steady state load testing, what is it is fundamentally try to run your load test at what we call the nominal pace or the nominal load. This is what you will have in production or what you will expect to have in production, right? So you have your system, they're not overloaded, they're working well, and everything is fine. This is how you expect your production system to work normally, right? And they give you interesting information, this kind of load test. But there's also limit load testing, and this is typically when you want to have and try to maximize or put one of the resources at saturation. And for example, it can be the CPU. You have small containers, maybe with just 3, 4 cores, whatever, and then you try to see, okay, can I get this container at 100% on all 4 CPUs? Or maybe it's not the CPUs, it's the network, because you are uploading, downloading big chunk of data. Or it can be the heap memory, or it can be application resources. For example, you impose a load and you want to monitor how's my database doing? Is it capable of sustaining the load? Or at this point, we do not have enough resources for the database, but the application, the web application, can actually sustain the load. And so on and so forth. There are, a bunch of different scenarios depending really on your application. So they are useful because both are useful because they give you fundamentally different metrics and different data. The steady state one is very useful for capacity planning, and so deciding how many machines do I need in production, and for scaling strategies. So that if you add one more machine, you will have this much capability to handle additional load. For limit load testing, however, you get a different set of problems and a different set of answers. In particular, what you get with the limit load testing is the behavior in case of saturation of one of the resources. And so this is very useful because sometimes you get a series of errors that are very common, that are specific when one of the resources ends, and you don't have any more of that. Another very interesting answer that you get from limit load testing is when you put the system into limit load testing, and then you remove the load. Can the system recover and go back to nominal pace if you apply again a nominal load and not a limit load? Okay, this is really important because certain systems cannot do that. So you have a spike of load, your system goes into a bad state, but then when the load finishes, your system cannot recover, and then you have to restart the server. Or you have to, take that machine out of the load balancer and spawn a new one or two. So these are interesting questions that you want to be able to answer in your case. So we have identified a series of steps that we recommend, that we do, and then we recommend to our clients to do, and I recommend here as well. Step number 1 is the setup. And by setup, what I mean is that you want to identify a particular hardware setup. What we typically use is one server machine, then we use one or more, typically many more, client machines. And then we use a dedicated machine that we call probe. That is the machine where you want to see how things look from the outside. So let me be more specific. Typically, what happens? You have a server, but the server is somewhere, and then you have loaders, and these loaders are really busy because maybe they're sending, I don't know, for example, for the typical Jetty setup, each loader goes at 60,000 requests per second. It's quite a big number, and so that loader machine has all the CPUs busy sending these 60,000 requests per second and parsing all the responses and computing a bunch of metrics and so on and so forth. So if you go to that machine and you say, oh, now I want to make one more request, maybe with the browser, whatever, and you want to see how fast the response comes back, well, you get a number, but that number is typically not what a normal user would experience. So if you have a distributed system over the network, and then one system loads, makes a new request to your system, even if your server is busy serving 60,000 requests per second, that one request doesn't really make much of a difference. But the client that is making that request is a completely idle client. It's a new browser from a new machine, maybe closed. And so what is it that browser will experience? It will see the response coming back immediately. Will see the response coming back very late because the server is so busy. So this is the role of the probe that we use. The first thing that you have to do, and we go in layers here, is to configure the operative system. In particular, what you want to configure is the increment the number of open files. That's typically something that is always forgotten, and by default, machines come with a very small number. And this very small number, it is typically like a big problem. If you deploy a server and the server can only has 1,024 open files, which in the Linux world means 1,024 sockets open, for example, well, you cannot open more than 1,024 sockets, and therefore you're somehow limited. So remember to tune that. Another thing that is especially useful for the client is the ephemeral port range. So if you're a client and you're opening 20,000 different connections, you need to have 20,000 different ephemeral ports on the client to be able to connect to the same port on the server, right? Let's say port 443 on the server, right? But you need the different sockets on the client, and each socket's 20,000 different sockets. Each socket is a local port that is different from each other. So you need to configure that. Another thing that is recent somehow is that we now have CPUs that are able to scale the frequency at which they work. It's now, many years that they are able to do that. And it's really important to, change this parameter and say, hey, okay, I don't want this parameter to be a variable when I do load testing. I want it to run at a fixed frequency. So the CPU run at this frequency, thank you, bye. And so you need to tune this kind of things. Then we go to the upper layer and we tune the JVM. And the things that you want to tune in the JVM is choose the JVM that you're going to use in production. That's a very important thing, because if you do a load test with 21, but then you deploy on 11, well, you get, I guess, surprises. The other thing that you need to pay very close attention is what is the garbage collector that you want to use. Our recommendation, especially for low latency applications, is to use generational ZGC, which is available on 21. The reason is that generational ZGC is awesome, and there's benchmarks that are being performed by the Oracle team that works on ZGC, and is just mind-blowing. So if you have this particular use case, go for that, but try others, because your mileage may vary. Your application may have requirements for the garbage collection that are met better by other garbage collector. The last one is the bag known safe points. Is a special switch that is particularly useful in profiling, which we'll see in a few slides. Typically, it has a little bit of a cost, but when you do profiling, it is very important to have this on. Next is, okay, so now that I've tuned the operative system and I tuned my JVM, what I need to do is I need to create a load load test scenario, right? Well, okay, so maybe you guys were expecting, oh, I'm, opening a terminal here and I'm showing you things and how this works and so on and so forth. But the reality of this thing is that this is what is really typical to you. So, for example, I can show you, and I will in a few slides, show you what we use for Jetty load testing. But that is typically not the scenario that you will have, because maybe your scenario would be, I want my user to land on the home page of my application, website, whatever, then download all the resources, which is traffic for the web server, then maybe log into the system, arrive to the product page, pick a product, and see the details of that product. And that is my most common use case that I want to test how performant it is. Or maybe you're not interested on this flow, on the whole flow, you're just interested in, oh, I want to know what is the performance of my landing page, so the home page of my site, and so on and so forth. So there's a bunch of tools that you can use to simulate all of this. We used a project that we built internally called the Jetty Load Generator. Based on, it's clustered, so it can deploy a server and all the clients and the probe. But there are other solutions like Gatling, which is written in Scala, or Hyperfoil, which is a solution from Red Hat. Other cloud providers also provide their own load testing solutions that you can possibly use. JMeter is a very famous one that has written in Java. It's an Apache project. You can write workflows and take metrics and everything from it. Work2 is written in C. There's many solutions around. You have to find what is the best for you. Typically, I've seen many customers using Gatling is particularly a favorite. For very high performance, I suggest Hyperfoil, because on the client side it does a bunch of tricks to have the client have the least impact possible, and so you are actually measuring real times on the exchange between the client and the server, and so on. So pick your tool, but there's many available. That's my point. So there's no excuses. If you really want to do a simple test, or you want to do a complicated test with a flow inside your applications, there are solutions available, and there's no excuse for doing that. This is the most important slide that I would like you to take home, and it is, when you do load testing, you need to do resource tracking. There's no way around it, and you have to track resources at every possible level, and as many of them as you can possibly think of. So this goes from the CPU, is it saturating? The network, is it saturating as well? I'm using a network and I'm sending down huge responses, or making big uploads. If the network bandwidth is completely saturated, there's not much that you can do. You can make so many requests per second because now you're blocked by the network, not by the CPU, not by other processing things that you have. If you use disk, for example, because you're accessing databases, is the SSD performance. And then in order to use all these things, it's like, okay, I want to also monitor hiccups that may happen on the operative systems. The garbage collector logs, I want to make sure how many threads is my server using for handling this particular load, how many connections, and so on and so forth. And then you want to gather, obviously, the response time and the type and the errors that you can possibly have in your load test, right? So this is really important. It takes time. Again, this depends really on your system, because it's very easy. For example, with JMeter, it has a built-in system to report response times, right? So JMeter makes a request, comes back the response, JMeter itself measures the time, there you go. However, that doesn't tell you how many threads you had on your server. Maybe you have particular subsystems on your server. So you land on a server, you make 4 requests to microservices. You want to know each microservice, how long does it take? And so you have to add some additional instrumentation to your code in order to figure that out, and so on, right? So it's not easy. So this is the typical setup. You want to have resource tracking. You have one server, many loaders, and one probe. Why the many loaders? Because the most common answer that we give to customers and people that opens issues to Jetty is, you are limited by the clients. The server can do a lot more. There's no problem. And, and that's it. So in our case, for example, we use 4 loaders, each one at 60,000 requests per second. So the server sees 240,000 requests per second. This is our, would say, nominal scenario, but at that load, the Jetty server that we have is at about 10% CPU. So the Jetty server runs a nominal load in that sense. And this is just because we don't have more machines, more clients' machine to actually impose the load. So this was an interesting finding. Once you finally set up all your things, the first and most important things that has been, and it's often forgotten, is establish a baseline. This is really important because the baseline will tell you, is my system configured okay? Does it really do what I need to do, right? And this is often overlooked, and people just say, just straight jumps into, okay, now I want to know how many, what is my maximum throughput, and without even checking whether the whole system as a whole actually works, right? So you really want to go there and say, okay, let's start small. Let's apply a small load. With this small load, I have expectations. I'm expecting to see, let's say, 100 connections being open to the server. I want to see at least 20 threads on the server serving requests concurrently. Do you see those numbers? Is that what you expect? And if that matches your expectation, you're fine. You have configured your system, everything works fine, and you can go into step 3, which is actually running the load test. So you run the load test, and you gather all the information. So what is the load that you're imposing? And then all the resource tracking that you get, you finish the load run, and then you have all your information about the resources. And then what you really need to do is, oh, by the way, do it both on the client and on the server, right? Because you want to test the server, but you really want to test the client, because sometimes the client, you think they're sending 60,000 requests per second, but they're not. Okay, and so you think, oh, my server is able to do 240,000, but really, maybe not. So both client and server needs to be recorded. And then what we suggest is to use this methodology introduced by Brendan Gregg, which is the use method. Use stands for utilization, saturation, and errors. However, it is best when used in the reverse order, only that the reverse order wasn't really that catchy of an acronym. Therefore, it's the use method. But really, what you want to do is, first, you look for errors. Do you get 200s from your requests? Because that is really important, because maybe all the connections are there, but you only get, and this is a story that actually happened to me. I set up all the system, run the baseline, and then change the URI. And by changing the URI, I mistyped the URI. And so I run the system, and I see an incredibly large number of requests per second. I say, oh, wow, the system is really, 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 really fast. Yes, but it was replying 404s really, really, really fast. So the 404s were interesting, but not that interesting for my use case. I have no, I was doing nothing fundamentally at the server side. So check for errors. The other thing that you can check is saturation. And remember that you really want to test for max capacity of every resource. And pay particular attention to the fact that most of the metrics that you get out of a system that you monitor, they're not particularly instantaneous resource consumption. They're somehow averaged over a period of time, okay? So pay a little attention. I have an example to show you later. And so that's the difference between saturation and utilization. Utilization is an average of, the usage of this particular resource over time. So the fact that you see 70% utilization of CPU means that in that period of time, the CPU was 70% busy, but what does exactly mean, okay? We'll see in a second an example. So now you gotta ask yourself the question, okay, so I got my number, everything figures, I have no errors, I got this many requests, this many threads, and this throughput. Is this number good for me, right? So you gotta go back to the initial questions that you wanted to ask when you wanted to do a load testing. And the initial question was, okay, what am I interested in? Capacity planning, I wanna check resources, I wanna be sure that my application behaves properly, and so on and so forth. And so whether the numbers are good or not, that depends on things. But then you have to figure out, okay, so how can I improve my number if they're not good, right? So if they're good, you can say, well, okay, fine, we've done a good job. We applied good techniques, writing the code and, caching things and not doing mistakes of, using global locks or things like that. So kudos. But if they're not good, then the question becomes, okay, now where do I look? How can I improve the system? And this is where we enter the last step that we suggest, which is profiling. Profiling, you want to choose. So basically, the idea is you attach a profiler to the server or the client or whatever you're interested in during a load test. And the profiler has to have this particular characteristic, which has to be asynchronous, meaning that it has to have a way to sample the threads in an asynchronous way. Many profilers by default do not do that, and therefore they apply to the system a huge bias. And so the numbers that you get out of those profilers, they're not good at all. Like they're garbage. You cannot say anything about what happens in the system. However, many of them have an additional option, or by default, they use this special call called async call get trace, and which is available, for example, in Async Profiler. By the way, the latest version of Async Profiler doesn't even use this secret call anymore. They have replaced the mechanism. Instead of calling this hidden API in the JVM, they now use a completely different mechanism to do it, and they can do it asynchronously as well. So once you have configured the profiler, you just attach it to your server, run the load test, and then gather the information. Typically, what you get out of an async profiler run is what is called a flame graph. I'm not going into a detail, but fundamentally, we'll see a couple of images later. But again, this is the work of Brent and Greg, and they're really useful because they really allow you to pinpoint what you need. So, right, so once you have a profiling session, you run the load, you see the flame graph, you find the problem, you fix the problem, you run again the flame graph, the load test, you produce another flame graph, you find another problem, you fix the problem, and rinse and repeat in this way, right? So it's a typical cycle of performance fixing. So let's go into some of the examples because, this is the theory, but let's see some real world examples. So this is a run where we wanted to do a limit load testing on the Jetty project, and then we wanted to increment the loader rate. We started at 60,000 requests per second. We wanted to go up until we wanted to see what was the maximum throughput that we could achieve on the server for the load that we had. So we arrive at 120K requests per second, and we have the CPU usage. You see the last column, it's all green, because the numbers that you see there, there are about 70-75% idle CPUs. Idle, meaning these CPUs were only doing 25% of work, 75% idle. However, if you notice, one of the CPU only has a 30% idle kind of number. Say, oh, that's kind of weird. But then we go to the client and we see this is the throughput of the client. The client was supposed to send 120,000 requests per second, but as you can see, it's kind of wobbly. It's not. I would have expected like a total flat line in there. And so we check with the use method and we say, okay, we see no errors. We see no CPU saturation because the server and the client were okay. I mean, those figures for CPU were on the client. and the network is not saturated, and all the parameters are nominal, the system seems to work really fine. But why do we have that wobbly, figure for the client? Well, we investigated this, and we say, oh, it's not that we have a problem with the CPU, because again, remember, when you see the utilization and you see the number like 34% average utilization of a CPU, it's an average. And so what was happening was there was one thread, and it was the sender thread on the client that was just spinning it out as fast as possible and could not do more than 120,000 requests per second. Sometimes it had to slow down. And so what we were seeing was that one of the CPU was basically at 100%, but from time to time, this thread was able to catch up, sleep for a little while, because the Jetty server is really fast, and this is like all in a local network. Therefore, send a request, sleep a little bit, send a request, sleep a little bit, and that was making 120,000 requests per second. So by sleeping, that particular thread could have been moved to a different CPU. And so because of that, you could see, oh, I have 75% idleness in all the CPUs. One of them is busier because sometimes the client would send a request, come back, do I have to sleep? No, because I'm late, I gotta send another request and send another request. I'm still late to send a request, and burn that particular CPU. Solution for this problem was, well, let's use 2 threads to send the load to the server rather than just one. So, simple solution. Let's go to another example. It took us like 1 week to figure it out. So we had this steady state thing, and then we just went there. And so the idea is that in Jetty, we have 2 thread configuration modes. And we wanted to test the difference between the two, like in the blind. We didn't know whether there was a difference, but let's say, okay, let's run one test with one configuration and one with the other, and let's see what's coming out, right? And so what was coming out was this. Every bar is the maximum response time within 5 seconds. So every bar is 5 seconds, and within those 5 seconds, there were a bunch of gazillion requests, and that is the maximum time that the slowest request took. So as you can see, the 2 graphs is really different. It's the same scale, but obviously the one below has higher maximums, right? But why? So we were there. Everything is the same. The time that it goes is like, we record the time here, we execute Java code, we stop the time there, and it shouldn't really matter what configuration of the threading system of Jetty happens, because no matter what we choose at the beginning, eventually we start parsing the request, and it's a thread in both cases, and the thread just goes on, calls the application, sends a response, and then we stop the recording, right? So why do we have such a big difference? Well, after 1 week of trying things and figuring out, we said, well, okay, let's not guess. Let's try to measure. And we enabled perfstat. And what we see was that we forgot to set the CPU governor to performance. So one test was running the CPU at 2.6 gigahertz, and the other test was running at 1.3. And so the second test was actually running slower because the CPU was running slower. And we had exactly solved the problem. You see the same number of cycles, just twice as slow. And that's why we were getting slower execution of the code. So governor to performance always, it's a good choice. This example, it's a typical example that we do for caching optimizations. So this is a flame graph that we got, and there's those 2 towers on the left. They're kind of weird. We're spending time allocating an exception, and we just remove the allocation by using a static exception, because we don't really need the stack trace. It was just an exception that we use internally by the code. And so now we have this flame graph, and the 2 compared. As you can see, the 2 towers on the left are gone, completely gone. And as you can see, the right side of the top flame graph now becomes the the one below just slightly larger because now I have all the free time that I can spend not doing allocation of I/O exceptions. So when you do profiling, this kind of things is really useful because you see, oh, what are those 2 towers? Why am I spending all the CPU there? And it's an easy fix. This one is an example where we did a performance-driven design of APIs in Jetty. And so really fast, we had this initial proposal where, as you can see, we had the handler class returning a processor, okay? So we were asking the handler, can you handle this request? Is this request for you? If not, you want to return a null processor saying, it's not me, I don't know how to handle this request, and the Jetty engine will return a 404, right? But then we had another proposal, which was this one. And this proposal said, okay, why don't we simplify things? Rather than returning an object, we return a Boolean. Is there a difference between the 2 APIs? Yes, there was a difference. So we tested this, and these are, again, the maximum on the bars. As you can see, it's eye to eye. It's not really clear which one of the 2 is better. But when we look at the numbers, we see that the version with the Boolean was consistently better than the other one, right? And so, like Greg Wilkins says, we're not really in the business of building and writing a web server. We're in the business of writing a fast web server. And so we decided, well, the previous API, the one that was a returning processor, was maybe a cleaner API from the design point of view, maybe more intuitive to use for people, but it was slower. So let's go for something that is slightly less intuitive, but still with documentation can be easy to understand, but it's definitely faster, okay? So conclusions. Load testing is hard, but there are tools around to do things. So do the steps that we suggest here. So set up, baseline, load run, and eventually profiling. Analyze the results with the use method. Always go and search what is the resource that has saturated and does not allow me to go faster or better or whatever. And you need to apply brain sometimes during the analysis because, you know, we ourselves have problems and spend just 1 week puzzling, okay, why is my Jetty server going twice as low? And then it just turns out that we forgot to do one of the configuration that were recommended in the setup even phase. So thank you for listening. If you have questions, I'll be around.